I'm Rohit Kumar Singh, the teaching assistant for this course, Accelerator Physics. It is being taught by Professor Amlendu Sharma, Professor Rajni Pandey, and Professor Pitamba Singh over NPTEL. And so on every Saturday, we'll have this live session with me. And in this live session, I'll try to recap some of the concepts for the given week, and maybe solve some sample problems which will help you in the tutorial assignments given on the NPTEL. And also you can ask any doubts or any general question that you have regarding the course. I'll try to answer that. So a bit of background about me. So I'm a PhD student, a PMRF scholar at IIT Madras. I'm in my third year of PhD. So, and I'm working in the field of high energy physics. So basically, I work with the collaboration of CMS experiment at CERN, which hosts the largest accelerator that we have, the Large Hadron Collider. I think you all may know about it, but I'm not working in accelerator physics. My research is mostly related to not to the hardware part of accelerator physics, but to you can say some software parts and then physics analysis. So what we do in CMS experiment, my group here at IIT Madras is we try to look at the heavy ion collisions in the LHC using the CMS detector, and we try to understand the properties of the matter created in those collisions. So the matter that we create there is called quark-gluon plasma, and it's a very exotic matter, and yeah, we study the properties of this quark-gluon plasma using the CMS experiment. So yeah, this is a bit of background about me, and if you guys are comfortable, I would like to know about you guys as well, because that will help me to to go on with this tutorial, this live session. Like if I know which background are you coming from, what type of training you have before, so that I'll keep my instructing level at that level, instructing level according to that. Okay, so can we start from Amit Sharma? Can you tell me about your name, what are you studying, and yeah, please. Yeah, good afternoon. Okay. MSc? Okay. That's great. Then we can go to Anagha. Good afternoon. Okay. Thank you. Then Dhanus Kumar. Yeah. Hi. Okay. Thank you. So yeah, 3 MSc Physics. That's great. Then Dominic. Oh, you are in undergrad. Okay. That's great. Then we can go to Pawan. Medical physics. Oh, okay. So my master's is from IIT Kharagpur. I know about this course, medical physics. Yeah, great. Oh, yeah, yeah, I know. Yeah, thank you. Okay, so then we can go to Pratibha. Good evening. Okay. Oh, you are studying civil. So may I ask, how are you interested in accelerator physics? Because it's a completely different field. Yeah. Yeah, that's yeah. Knowledge has no boundaries, right? Yeah. Okay. Great. Then Sahil, can you tell me a bit about you? Hmm. Okay. Okay. Then Sikha. Hello. Sikha, can you hear me? Okay, I think some issue. So maybe we can go to Viswas. Good evening. Oh. Uh-huh. Oh, that's nice. Okay. And then yes has messaged that he cannot speak. So maybe you can write in the chat. Oh yeah, you have written. Okay. I'm pursuing integrated MSc from okay, Central University of Rajasthan. Okay, then you are also MSc. Yeah. Hello. Who is it? Oh, hi, Sikha. Hi, you're back. Okay. Can you tell me? Good afternoon. Yeah. Mm-hmm. Okay. Okay. So you're from computer science background. Okay, that's great. Okay. So okay, thank you all to introducing yourselves. I'll request everyone to mute yourself because then you might get interference. And okay, so yeah, I see that most of you are from physics background, but some of you are from different backgrounds like computer science, civil, and yeah, and medical science. Okay, so it's okay. This course is not uh, that much of theoretical physics oriented, I would say. It's mostly about uh, you know. I think the prerequisite is basic physics course, uh, not some high level courses like quantum mechanics, these and other things you don't need these things. There are some concepts that from quantum mechanics, but they won't be much. Uh, so yeah, we'll see. We'll explain as we go along. And yeah, okay, then let me start today's live session. So yeah, when we talk about accelerators, so why we need accelerators actually? The main question is, I guess, why accelerators? Oh, sorry, writing away on the pad after a very long time. So why accelerators? Okay, I'll try to do it better. Okay, so yeah, so why do we need accelerators in physics? So I think the story goes back to like 1930s, uh, when the first accelerator we had was used to split the atom. You might have heard about it. It's called uh, Cockcroft Walton accelerator. So the two scientists, Cockcroft and Walton, built it, and they used it to split lithium atom into two helium atoms. So that was the beginning of accelerator uh, at high energies, uh, and they got the Nobel Prize for it 20 years later. So yeah, that so this was the start. But nowadays accelerators are used in many fields. For example, so mostly it is used in high energy physics, the research that in which I am involved, and to probe much deeper inside an atom. So inside an atom there is a nucleus. Inside the nucleus there are protons, neutrons, and inside those protons, neutrons there are quarks. So with the help of accelerator we can probe deeper and deeper inside the matter, and we can get some information about the basic building blocks of this universe. So these are the this is like the big picture of why we use accelerator. But there are many applications of the accelerator in our daily lives also, like so is it Pawan who is doing medical science at IT Kharagpur? Yeah, so you can say that there are many applications of accelerator in medical science also, right? For like proton therapy, and so to remove the tumors and all, and material scientists, yeah, and material scientists are also using accelerators nowadays to study the properties of condensed matter. And yeah, there are various things that you can do with accelerators. Okay, so I'll focus mainly on the physics part, which is the fundamental physics part. So we know that there is a de Broglie wavelength associated with every mass particle. So it's given by lambda equal to h by p, where p is the momentum of the particle and h is the Planck's constant. So and we know that the momentum is directly proportional to energy, so we can write it as 1 by e. Okay, so this means that if you want, if we go to a higher and higher energy, if we increase the energy, okay, so if we increase the energy of a particle, okay, somehow, then we can get a very small lambda of that particle. We can get a very small de Broglie wavelength. So this is the basic principle why we use high energy accelerators, why we accelerate particles to high energy. Because if you want to study matter on a very small scale, so for example, if you want to probe inside a neutron or proton, which is of a scale of 1 Fermi, so we need a particle with de Broglie wavelength of this magnitude, okay, and for this we need a high energy. So the higher you give, you accelerate a particle at higher energy, more its de Broglie wavelength gets very small, and then you can probe a very small part of the atom, and it will give you information about very small constituents of the matter. So this is the basic principle why we have high energy accelerators. Sorry. Okay. Setting is off. Yeah, we're back. Okay, so does everyone understand this concept, or anyone has any doubt? You can ask anytime. Okay, thank you. So, and then yeah, so this is the basic concept about accelerators. And so for then there is one more concept that we have. So you know the energy and mass relation from Einstein, the famous E equal to mc square. but the original one is gamma mc square. M is m naught. So gamma is so gamma is the relativistic factor. It is given by 1 by 1 minus v square by c square under root, and m naught is the rest mass of a particle. Okay, so now we talked about increasing the energy of a particle. So what can happen is, so if we increase the energy of the particle, so we can write this equation like this: m naught by m naught c square by 1 minus v square by c square. Okay, so you see, if we increase the energy of the particle, what will happen? So because it is directly proportional to the rest mass of the particle, the mass of the particle will increase. Okay, and hence we can go up to so for example, at LHC, when we collide two protons, so normally the protons has one proton has rest mass of what, about 938 MeV, I think, right? But the collision energy that we get at LHC is around 13 TeV. Okay, so this energy is achieved because of this property that the energy can be converted into mass, and mass can be converted into energy. Okay, so yeah, and and we use this concept in many ways. So for example, we also collide heavy ions at the LHC. So you take a nucleus, so for example a lead nucleus, and you strip all of the electrons from it, and then you accelerate it up to a high energy, and you get collision energy of about 5 TeV. Okay, so yeah, these are the state of the art accelerators that we have right now. So let me show you a diagram of what we have at LHC. So you can see in this diagram, this is a bird-eye view of LHC. So it's a 27 kilometer ring in which we accelerate the protons. But before going to this bigger ring, we have many stages here. So yeah, this figure is a little overwhelming, but I'm just wanted to give you a feel of what it takes to build such a high energy accelerator. And so basically, before you go into the bigger ring of LHC, you have many stages which boost the energy of the particles stage by stage, and then you get such a high energy of like 13 TeV or for protons, and 5 TeV for ions. So yeah, it's a really a great engineering marvel, as well as very advanced machine, I would say. And yeah, this is the tunnel, inside the tunnel image of LHC, and you can see the beam pipe in which the protons are accelerated. It contains thousands of magnets and dipoles to accelerate and focus the beam. So yeah, you can read about it. It's a very interesting experiment. So, but before understanding these things, we'll go step by step. So the first accelerator that we had in the history. Let me go to full screen. Yeah. So the first accelerator that we had was, as I mentioned, it was called Cockcroft-Walton accelerator. Okay, and sorry, I think this is the correct spelling. So yeah, it is basically a one more thing I want to know. So have all of you gone through the first week lectures on the NPTEL? Okay, maybe you can write in the chat how many of, so that I can get an idea, like are you completely new to this or you have some background? Can you write in the chat yes or no? Have you, okay, one yes, two yes, okay, four yes, okay, I think, okay, one no. Okay, I get the idea. I mean, okay, so I'll try to keep it. So my job here is to mainly recap the concept, but I'll try to explain some things. Okay. So yeah, so this accelerator. So basically, this accelerator is consist of a generator. Okay. So what does a generator do? A generator provides you a voltage, right? It provides you a potential difference. So how does this do that? So this Cockcroft-Walton accelerator consists of a simple, a voltage multiplier. Okay, I hope that all of you are familiar with some basic electronics. Okay, so and we use AC voltage to charge some capacitors in parallel, and so how do we do that? So before understanding the big accelerator, so let me start with a simple circuit. So suppose you have a AC applied, okay, and it couples to the circuit, and you have a capacitor here, and so when you are using an AC to charge a capacitor, you cannot use resistors. So anyone knows why we can't use resistor when we are using AC power? Can anyone answer? So these are diodes. Okay. So yeah, great. Yeah, you're right. So yeah, because we have AC, for first half we have a current in this direction, then the current changes its direction. So if you are using a resistor, then it will charge the capacitor, but in the next half it will just discharge it. So we don't want that. So that's why we use diodes. And so the diodes has this property. So when a diode is forward biased, so like this, so this is positive negative, which is connected to positive and then negative. So this is in forward bias state, it will allow the current to pass. Okay, but if we reverse the direction of the voltage, so for example, if we keep it in this state, then it is reverse biased and the current will not pass through it. Okay, so no current. So now you see this circuit. Okay, so now you focus on this circuit. What is happening here? So when we have positive voltage here in the first half of the AC cycle, this one is forward bias, this one is reverse bias. So the C1 will get charged up to a certain voltage. Okay, and Then in the second half of the cycle, what will happen is this one will be reverse biased, and now this one will be forward biased. Okay, and so the current will pass through C2 and the capacitor 2 will get charged. Okay, does anyone have any problem here? Everyone understand this, right? You can ask if you are having some issue. I can explain more. Okay, if not, then okay. So this is a simple circuit with capacitor and diodes with AC power. Now what we have in a Cockcroft-Walter accelerator is something like this. So again we have a AC source which couples to the circuit. I'm not going to draw the whole diagram, I'm just trying to give you a feel. So here we have a capacitor, then you have a diode, here you have a capacitor, then here another diode. So I don't know if I'm drawing the diagram correct, but I just wanted to give you a feel of what how does this work. So yeah, so and this is the AC source. Okay, and so like I said here, so for example, so suppose now in the first half of the cycle, when we have this terminal positive and this one is negative, okay, so this one will be reverse biased, right? This one will be reverse biased and this one will be forward biased. So the current will pass through this capacitor and then through this circuit like this. Okay, and so this one will get charged, this capacitor and this capacitor will get charged, and in the next cycle the C2 will get charged. Okay, and so this unit is repeated okay, several times, and you get a potential of so for example here you will get, so if the signal AC signal has this kind of form where V naught is the magnitude, you will get a 2 V naught at this stage, and then as then you add, if you add another stage, you will get 4 V naught and so on. So the maximum that you will get is 2 N V naught, where N is the number of stages. Okay, number of stages. So in this way you can get a very high voltage using this kind of circuit. But now you will say that why can't we go higher and higher and get an infinite voltage? So can anyone tell me why we cannot do that? Why we can't have infinite voltage adding infinite circuits like this? What? Yeah, you're right. Yeah. So at some stage we are going to have a dielectric breakdown. So yeah, we'll have to be careful. Okay. So then, and then what we do is we apply this potential. So the voltage gain that we get, we use this in our accelerator. So we have, so we can couple a linear accelerator like this, and which will have a source here, so some ion source or something, and we can apply this voltage here, and we can so you know that charged particles accelerate when we apply a potential. So for example, you know that So you know that if you have two charged plates, so like in photoelectric effect you have studied, and suppose you have a charge here, and you applied a potential V, so it will gain a kinetic energy, and so suppose it's a positive particle, sorry, let's make it negative, and this is a positive and negative diode, yeah, diode, and then it will gain a kinetic energy of QV, right, when it goes from here to there. So this thing we can do with this generator. We can apply this huge voltage that we have created here to a linear, to a to a tube with an ion source, and we can accelerate the ion. We can give kinetic energy to the ion, and so that was used by these scientists Cockcroft and Walton to create a beam of ions, and they bombarded that. So they created a beam of protons, and they bombarded on a lithium atom, Li7, and they got 2 helium-4 atoms. So they splitted the atom basically. And yeah, they got Nobel Prize in 1951 for this. So, but yeah, now we have come a long way from these basic accelerators. But as I mentioned, so every big accelerators has some components which uses this kind of linear accelerators using potential difference. So for example, at LHC also, you can maybe you can see we have this LINAC here. It's a linear accelerator. This LINAC 3 and 4 we have here. So these are the starting point of every beam, every proton beam. Okay. First we have a linear accelerator which uses some kind of some similar concept like Cockcroft and Walton accelerator, and then we send this into bigger colliders like proton synchrotron or SPS, super proton synchrotron, and then in the LHC. But the starting point is always some linear accelerator. So that's why it's important to understand how a linear accelerator works. Okay, and okay, then I'll maybe quickly write some relevant formulas that we'll use in the problem. So yeah, so when you apply this voltage to this accelerator, the effective voltage that you will have is given by, so you have this maximum voltage, okay, 2 and V naught, and then you will have some voltage drop because basically you are accelerating, you are sending currents inside the accelerator, and so that will cause a voltage drop, and there is something called ripple voltage. So this is the voltage drop, and this is ripple voltage. So this ripple voltage basically comes from because there are many components, many electronics components, and many things are there. So there can be some fluctuations in the voltage. Maybe it can increase by some amount, it can decrease by some amount, and so it depends on the number of stages that you have. If you have a large number of this stage, then you will have a larger fluctuation. So for example, this their expression is given by this formula. So C 2 by 3 n cube. So n is the number of stage, 3 by 4 n square, and then 1 by 12 n. And f is the frequency of the AC the oscillator that you are providing, and C is the capacitance. Then you have ripple voltage, as I mentioned, is it's directly proportional to the number of stages, and the order is n square. So for each new stage you get n square of dependence. So yeah, it really it scales really fast as you go to higher number of stages. And if you're using a higher frequency, then this can be decreased, but yeah, then so you have to optimize these things so that you don't get a much higher ripple voltage, because then you don't have a precise control over this ripple voltage, so you want to minimize it. Okay, so yeah, that's all I wanted to recap. So anyone has anything to ask here? Does everyone understood? Yeah. Yeah, beta is V by C, right? So the gamma is 1 minus 1 by beta square, okay, and beta is V by C. Is it fine? Okay, any more question? Okay, if not, then so now let's try to solve some simple problems, and it will be great if you guys also try to solve it on your own, and maybe you can interact a little bit more. Okay, so the first problem is so the question, one more thing, can you read the question well? The font size is low. Is it fine? Okay, thank you. Okay, so the question goes like this. So the Higgs boson, so you know about this discovery at LHC, the Higgs particle. It was discovered in 2022 at LHC, and so the LHC was LHC was basically built for discovering this particle. It was a last puzzle piece in the standard model of particle physics, and with the discovery of this, the standard model became kind of complete. I mean, it's not really complete, but yeah, it is now consistent. So yeah, this Higgs boson discovery was a very crucial for the field of particle physics, and it has a mass of about 125 GeV. Okay, so it's really massive. So compared to a proton, so proton has a mass of 938 MeV, right? It is about 125 times heavier than a proton. So it's the rest mass of Higgs boson. Okay, and this was produced on the collision of two protons. So when two protons collided, it produced it produced the Higgs, and then Higgs decayed into G bosons and some more particles, and we can detect G boson decays into gamma, I mean the photons, and we can maybe then reconstruct the Higgs boson from there. So yeah, so the Higgs discovery was made in 2012, and as I mentioned, the proton has a rest mass of around 930 MeV. So if you add up, so for example, you have two protons, right? So you got only around 2 GeV of energy, around 2 GeV of energy, right, in total. then how can a 2 GeV energy can produce a 125 GeV particle? Right? So, but it does. So, like I mentioned, how it does. So you basically you accelerate these particles up at higher and higher energy, and they get massive and massive because of this relation. Okay, and you what you get at the end is a center of mass energy of the order of TeVs, like 10 TeV. Okay, so then when they collide at this high energy in the order of TeVs, they create many particles with energy of the order of GeV. So yeah, that's what happens at the LHC every time. So then the correct option will be here, just the A. LHC has related protons to TeV energy. Okay, I mean it also uses a high magnetic field, but that's not how it accelerates to TeV energy. Okay, so yeah, this is a simple fact. Then another simple problem. So I just wrote this equation. So in Cockcroft-Walton accelerator, the voltage ripple is proportional to C H. So what is the relation? What is the correct option here? I have just wrote this equation. Anyone? No. What was the ripple voltage? It was 1 by Fc, right? Yeah. So the B, the higher the capacitance, you have low ripple effect. Okay, then third problem. So here, if an AC voltage source having frequency f is used in a Cockcroft-Walton accelerator, is it possible to charge the capacitor to high voltage and retain it if the charging is done through resistors? So I discussed this, right? So now you tell me, what is the correct option? So first of all, read the question carefully. So is it possible to charge the capacitor to high voltage and retain it if the charging is done through resistors? Think again. Okay, someone has said C. And anyone else? Some A, okay. B, okay. No one is going for D? Okay, so yeah, like I mentioned, so if we use, so suppose you have a AC source, you have some capacitor, and you applied a resistor R, okay. Then, so suppose in this cycle, so a resistor has nothing like reverse and forward bias thing, okay. It allows current to pass through every direction, okay. So when in the first cycle, when this is positive and this is negative, the current will flow like this, right? The capacitor will get charged up to a certain value, okay. Suppose it will get charged to Q, right? And then in the next cycle, when this one is positive and this one is negative, the current will flow like this. And so whatever the charge that has been accumulated here on the capacitor, it will get discharged, right? Because the current has reversed the direction. So this Q is Q is given by V by C, right? Oh, sorry. is it C by V or V by C? I forgot. So V is Q by C, so Q is V by V CV. Okay, sorry, Q is just CV. Yeah, so it depends on the voltage, right? So if you have if this and basically you have a delta V, so for the current going this side it will be positive, but on the other side it will be negative. So whatever charge that has been accumulated will get just cancelled, right? You get 0. So you cannot charge the capacitor using a resistor. Sorry, you can charge it, but you cannot retain it. Okay, if you just if you switch off here at half of the cycle, then it might stay charged, but then it will decay. The charge will slowly dissipate. So yeah, retaining it is not possible if you have a resistor. It can get charged, but it will not, but can't retain it. The C option is correct. Okay. Everyone understand? But once again, okay, let me explain it this way. Okay, so now if instead of a resistor you have a diode, now what will happen is, for the first cycle, when this is positive, this is negative, the current will flow. Okay, this capacitor will get charged to a Q value, right? And in the next cycle, because this one now is reverse bias, it will not allow the current to flow, so no current from this side. Okay, so whatever charge that has been accumulated here stays here, right? And then again in the next cycle it will again get charged to 2Q and so on. You see, the charge will keep on accumulating. But if you have a resistor, like I explained, it will allow the current to pass through both the sides, and whatever you gain at one half cycle will be lost in the next half cycle. So it will be just loss gain. You cannot retain the charge. Understand? Okay. So anyone else has any doubt? Okay, then if not, we can go to the next problem. It's moving. Okay. Now the fourth problem here we have is a proton moving with a relativistic factor 0.948. Okay, what will be its kinetic energy? So you have a proton, okay, and we know the mass of the proton. It's about 938.272 MeV. I'm writing this in MeV per c square, okay, because the answer is in MeV, so it will be easy to calculate. Okay, so this proton is moving, and we have given the relativistic factor, which is 0.948. Yes. So the relativistic factor is beta, right? Or should it be the gamma? It should be beta. Beta is V by C. Because beta is V by C. Yeah, gamma is always greater than 1. So yeah, it is beta. Okay. Then so we have to calculate kinetic energy of this proton. So how can we do it? Anyone has any idea? So normally in classical mechanics, what we have, the formula for kinetic energy, it's just mv square, right? But this one is not valid here in the relativistic case. It's just an approximation of a relativistic formula, not valid in relativity. Okay, so then how do we calculate the kinetic energy? Anyone? I cannot hear you well. You are saying under root plus, wait, minus m naught square c square, right? Or c to the power 4. Oh, c square, c to the power 4. Okay, then plus p square c square. Plus, oh, okay, so this is it, you are saying. This is the kinetic energy, this is the total energy minus rest energy, this one, right? Okay, yeah, your logic is right, because we need kinetic energy, so we can have this total energy minus rest energy. But so we have been given here this beta factor only, and we know the mass only. So how do you calculate the momentum? We have been not given the momentum, right? Okay, so yeah, I mean, this formula is the formula that you that you wrote was correct, but we can write it in a different form. So kinetic energy, as you said, is the total energy minus rest mass energy, which is m naught c square, and then we can write the total energy as gamma mc square minus m naught c square, right? This is the total energy. You can write the total energy like this, correct, for any particle. And then you can, gamma m naught, and then we can take the m naught c square odd, and we have gamma minus 1, and then we know that the gamma is given by 1 minus beta square minus 1, correct? Correct. Now you have everything. You have the rest mass of the proton, you have the beta given to you, so you can just put them. So the rest mass is 938.272 MeV by c square into c square, so c square just get cancelled. Then 1 minus 1 by 1 minus your 0.948 squared minus 1, and you can calculate this. You can use a calculator, and you will get answer close to 3901 MeV something. Okay, so yeah, the B option is correct. So, is it fine? Everyone understood? It's a simple calculation, you can do it. Okay, if it's fine, then let's move to the next problem. Okay, this is a non-calculative problem. So the question is, the DC accelerators cannot be made circular because there are three options. One is focusing will be disturbed. Second one is the electrostatic field is conservative. And the third option is charged particles radiate energy while bending. So what do you guys think? Which one is correct option? Anyone? A, okay. Focusing will be disturbed. Then by the way, do you know what focusing means? Not quite. So, I mean, yeah, the goal is to strike the target, but sometimes you don't have a fixed target. You have just two beams also inside the accelerator. So then, what focusing means? So you have suppose two proton beams, okay? So in the accelerators, there are not just two protons that are sent around, because you cannot isolate a proton like this. So you have bunch of protons, okay? So bunch of protons like this going in this direction, and then you have bunch of protons like this coming from this direction, okay? These are called baskets with proton bunches, okay? And they collide with each other. So the focusing here means is that, so suppose this is the beam axis, okay? So you have to really squeeze them together, so that they're not they're not that much expanded into the in the space, because it might happen that they will just cross each other without colliding, if they are that much far apart, or diffused. So that's why we focus them, and we squeeze them in a small part, so that they become very dense, and then we collide them inside our colliders, okay? So this is what focusing means. We use various kinds of uh, devices to focus the beam. Mainly we use electric quadruples, and yeah, there are many techniques to do that. So focusing will be disturbed. Okay, anyone else? Any other option? Hello? So what about the option B? Oh, sorry. What about the option B? A is not the correct option. Focusing has nothing to do with circular as accelerators. I mean, you can always focus the beams, because in any accelerator, because you have to just apply a electric quadrupole around the beam axis, and then you can focus the charged particles that you isolate. And the option C is charged particles radiate energy while bending. Mm-hmm. Okay. Yeah. Okay. So so the technique that we use to focus, so there can be many techniques. So the most uh, famous one that I know is this electric quadrupole. Okay, so you have an electric quadrupole, positive, negative, like this, around the beam axis. Okay, around the beam axis, and since these are charged particles, the force that an electric quadrupole applies over the charged particles is directly proportional to the distance of these particles from this axis. Okay, so now you see what will happen. The particles which are very far apart from the beam axis will experience a larger force in the direction of the beam axis. Okay, so they will move towards the beam axis while going around, while accelerating forward. It is just a perpendicular force that the electric quadrupole will apply. Okay, and this force is directly proportional to the distance of the separation from the beam axis of these particles that are going around. So they will move towards the beam axis, and they will get packed in a very small volume like this. So this is suppose the beam axis, and you will get a very dense kind of cloud of protons or whatever that you are accelerating, and so that's how you focus a beam. Okay. Yeah, it doesn't matter, obviously. So yeah, A is not correct. So okay, if no one has any more answers, maybe I can explain. So yeah, C is also not correct. Charged particles does not radiate energy while bending. Okay. The correct answer is the B, because you see what we have in a linear accelerator. Suppose we just apply a potential difference, some potential difference here, from here, and we project a charged particle from here, and it will get accelerated here. Okay, we can keep a target here where you can come and collide. But in a circular accelerator, so the charged particle has to go round and round. Yeah, like this. And if you have if you are using a DC current, DC source to accelerate the particle, so what you can do is you can enclose the beam pipe inside a semi spherical chamber made up of a metal, and you charge them. So keep them positive and keep this negative, and when the charged particle when the charged particles move from here to there, it get accelerated, right? But again, when it goes around, so this one is positive, this one is negative. Whatever acceleration that you gained here will be lost here, right? It will, because the charge is constant, right? If you have a positive particle, if you have a negative particle like electron, it will get accelerated here, but it will get deaccelerated in this part here, right? You understand what's happening? So that's how that's why we cannot have a circular accelerator with DC. But if we have an AC source whose polarity changes every time in a fixed cycle, So we can adjust this. It is okay. So what we can do is, if you have an AC source, you can adjust the cycle such that when the electron is coming from here to there, you have a positive potential here, negative here, and then when it goes around, come here, you switch the polarity, right? So now this one become positive, this one negative, so it again accelerates, and so this keeps doing that, and it will gain energy, higher and higher energy. So this is the concept of cyclotrons, where we use a AC electric field to accelerate the particles. But you cannot do this with a DC voltage. Okay, you understand? Yeah. So obviously, so the Lorentz force is just QE, right? If you don't have a magnetic field, this is charge and the electric field, right? And so the electric field is given by what? So the voltage that you apply will be converted into an electric field, which is sorry. My iPad is behaving like this. Sorry. Yeah. So Lorentz force is simply this. Okay, this is the charge of the particle, and then this is the electric field, correct? And if you have a negative charge, so suppose you have an electron, it will just so let's say minus Q times E, right? And so you apply some potential difference, some voltage across these two plates, and that will create an electric field. Okay, and so you exert the force on the charged particle, and force is what? Force is just m into A, and you get an acceleration like this, right? So this is the acceleration that you get. But again, when this charge goes to the around, and now at this point, what will happen is the electric field direction is switched. So whatever acceleration that you gained here will be lost in this part, right? So that's how. That's why you cannot use a DC source to accelerate the particles in a circular accelerator. You get the point? Okay, then let's move to the next problem. This is a simple fact. If there are n stages in Cockcroft-Walton accelerator, then the maximum voltage achieved, what was it? Anyone remember? So if you have a voltage like this, okay, what was the maximum voltage achieved in a Cockcroft-Walton accelerator? I wrote this a while ago. 2 MV. Yeah, correct. Okay. Then next problem. Okay. So in a colliding ring experiment, so colliding ring means a circular accelerator, right? E1 and E2 are energies of two colliding beams. Okay, so one beam is coming with E1, another one is coming from another direction with E2. Okay, so the center of mass energy is, so we have to find the center of mass energy, or let's write it EC1. Anyone has any idea what this is? So there are four options: E1 minus E2, E1 plus E2, E1 into E2, or E1 divided by E2. So anyone would like to answer this? Okay, anyone else? Everyone agrees with this answer? Okay. Okay, yeah, you are right. It's E1 plus E2 simply. Yeah. But then there is a question that I want to ask you guys. Why we need two colliding? Why we use two colliding beams? Why can't we just keep one beam and maybe fix the target somewhere, so that we don't have to accelerate both the beams separately? Anyone knows the answer? Why can't we do that? I mean, why don't we do that? No, this one is convenient, right? You just fix the target somewhere. If you want to collide to proton, if you want to have a proton-proton collision, you just move around one proton bunch and you keep the other proton bunch fixed at somewhere in a box. Okay, and then you cut the half price of LHC. I mean, because in LHC you have two different beam pipe going in different directions, so it's just the double of the cost. But then what's the disadvantage? What's the main disadvantage that you get? Yeah. Yeah. So yeah, let me write the so for a colliding ring, so for a two colliding beams, you have the total energy given by E1 plus E2, right? And if you fix the target, okay, if you fix one target, then the total energy is given by the expression, which is 2E1 into mc square. Okay, the energy of because it's this is the energy of the rest target, and this is for the beam, the energy of the beam. Okay, so now you see what is the difference here. So suppose you have same energy for two beams here that are colliding, then the total energy will be what? It will be 2E, right? And here you have, suppose, same energy of the one beam that you are striking on the target. You have 2E m0 c square. Okay, now you want to increase the energy of the beam by, say, twice. Okay, you want to increase it twice, so you make it 2E. What will happen in this case is that you will get 4E, right? Just increasing twice the energy. But here what will happen? So in this case, the new energy that you will get will be just under root 2 times of the old energy, right? So it's a very significant increase compared to here, where you have got 2 times increment in the energy. So this way, I mean, it's not it's not very beneficial to use a fixed target experiment if you want to achieve a very high energy. Okay, this can be done only in a colliding beam experiment. So that's why we go to extra mile and build accelerator with two different beam pipe which collides beams in moving in different direction. Okay. Yeah, so everyone understood this? Okay, so then let's move to the next problem. So for relativistic electrons at high energies, there are 4 options. Okay, so we are talking about relativistic electrons, okay, at high energies. High energy here basically means relativistically high energy. Okay, so if you increase so the velocity increases very fast as the kinetic energy increases, the first option. Then the second option is the velocity does not increase very fast when the kinetic energy increases. Third option is the mass increases as the kinetic energy increases, and the last option is the mass does not increase as the kinetic energy increases. So which option is correct? Please vote. Okay, both A and C. So you're saying the velocity increases very fast as the kinetic energy increases as well as the mass increases. Okay, anyone else? Yeah, same. Okay, anyone? Okay, so let me say so only this option is correct, the C. Okay, the velocity does not increase very fast as the kinetic energy increases. The reason is that you know that there is a limit to what velocity one particle can attain, right? If a particle has mass, so electron has mass, right, and it cannot go up to a speed of light. Okay, once it reaches near the speed of light, the velocity, to increase a very little bit of velocity, you need a very large amount of energy. Okay, so I mean this calculation you can do. I mean it's in the books it's in the book of Robert Resnick relativity book. There is a very beautiful calculation done there where it is shown that the velocity increases velocity increases very slowly. It almost gets saturated. Okay, so there is a plot like this, you know, this kind of this. So this is the speed of light limit. Okay, and this is the energy here on the x-axis. So if you increase the energy, initially the velocity increases very fast, but once it reaches near the this speed of light limit, it kind of saturates and it never really touches this limit. Okay, it's an asymptotic condition. So yeah, so what happens then to the energy? Where does this kinetic energy go? So it all goes to the mass of the particle. So so this was the expression for kinetic energy, right? Not c square gamma minus 1. So all the kinetic energy that you are increasing is going into the mass of the electron. So the electron will get massive and massive, but its velocity won't increase further. Okay, it will go to like 0.9999999 c, but it won't reach c or further than c. So this is a fact of relativity. Okay. Okay. So then, yeah. So then the ninth question. So electric fields are used for, there are four options: beam acceleration, focusing the beam, separation of different mass ions, acceleration of neutral beams. Anyone? Yeah, beam acceleration. You can use electric field for beam acceleration. Then anyone else? What else we can do with electric fields? Can we separate a different mass? Yeah, Amit, go on. We can separate different mass. How so? No. So you know the Lorentz force depends only on the charge of the particle, right? Not on the mass. Yeah, that's what I'm saying. If those all the ions have same charge, okay, so even if they have different mass, they will move with the same velocity in electric field. I mean, they will get the same. They will the same force will be exerted on them. And we cannot accelerate neutral beams also, because electric field is only applied on charged particles. What about focusing the beam? Just now I explained, right? So this one is also not correct. So you can use it for focusing and we can use for acceleration, right? So yeah, these two are correct. Okay, think about it. Okay, then let's move to our next question. I think we have 2-3 more questions, so we have to do over soon. Yeah, it's a problem from RC circuit. So yeah, I just wanted to remind you, because this kind of circuit will come later in the course. So you know what's an RC circuit is, right? You have a resistor and a capacitor, and you can charge the capacitor using a voltage source, and you can then it will get discharged. So the problem is so the options here, let's read them. So capacitor will be charged to 63.2% of its maximum value when the time constant, so the time constant tau RC is equal to 1. Then which of these options is correct? Okay, so you have to find out. Then the second option is capacitor will be charged to its maximum value, or capacitor will be discharged to 36.8% of its maximum value. It will neither be charged nor discharged. So anyone know how to solve this problem? Okay, second option, how could it be? How do you get this option? Do you have any formula? Q0 1 minus. Hmm. Okay, T by CR. Okay, just wait. Okay. So you're saying this is the formula for charging, right? Okay. So now let's put RC equal to 1 here. Okay. So it is just minus T, right? E to the power minus T. So then what will you do? Oh, sorry. Ah, time constant is 1. Yeah, it's fine. So how do you know it will charge to maximum value? So yeah, so let's so when we are charging, let's take the time to infinity, right? That's what we do, right? And if we take the time to infinity, what will happen? 1 by so yeah, it is 0. Sorry, Q naught. So the capacitor will be charged with maximum value, which is Q naught. Is it right? Yeah. Yeah. Because we are charging, so what time we just apply the voltage and we let it charge. Infinity is what we got, what we can put here. We don't have any other time reference, right? We let it charge up to how much, as long as we can. We just want to know, like, what can happen if the time constant is 1. How much will it get charged? So it will charge to a maximum value, which is Q naught. Correct? Yeah. Okay. Then next problem. Okay, so this is again from Cockcroft-Walton Accelerator. So if there are n stages in Cockcroft-Walton Accelerator with F as the frequency of the input voltage source and C is the capacitance of each capacitor, then the ripple in the voltage is proportional to. Anyone remember the ripple voltage expression again? D, right? 1 by FC. The ripple voltage was proportional to. Yeah. Okay, it's nice. And then I think it's the second last problem. Okay, again from Cockcroft-Walton Accelerator. So using Cockcroft-Walton Accelerator, 14 MeV mono energetic neutrons can be obtained. So using either a deuterium reaction or deuterium-tritium reaction, both, none of them. Do you know about this? Which reaction can be used to D? Yeah, I think it is in the lectures. So if you have gone through the lectures, yeah, you're right. So do you know why? Why deuterium cannot give you a neutron with 14 TeV energy or 14 MeV energy. What's the problem? Now, what determines this, the energy of the neutron? Do you know? So there is a thing called Q value of a reaction, right? So for this case, deuteron case, the Q value is very low. I think it's around 2.7 MeV. So, and this Q value is all that's available for the neutron to take away, okay? And in the case of deuteron plus tritium, the Q value is 17.6 MeV. So here it can take away 14 MeV and it can go fly away, okay? So this Q value is what determines the energy of the neutron that is being produced. All right. Oh yeah. So so there is I forgot the formula. There is a formula. It depends on the mass of both, mass ratio of the two products that we get in a reaction. Okay, 1/4 or something. I just forgot the formula, but it depends on the mass. Okay, because neutron is much lighter. I mean, much lighter than a helium, so it will get the more fraction of the Q value. Okay. If you have two neutrons here, then it will get equally divided. The energy, the Q value will get equally divided. Correct? Yeah. So I don't remember the exact. Yeah. Go on. Yeah. Just from the you can solve the. You can write the energy and mass conservation. You can do the energy and mass conservation. You can get this formula. Yeah. Okay. But it depends on. So the most important thing is depend on the mass, the products. Okay. Now so 13th problem. Oh, this is the second last, I guess. So in collision of two high energy protons in a colliding ring, antiproton can't be produced through the reaction that we have here. So what is the reaction? So proton going to proton plus antiproton. Because why this cannot be produced? So this P bar is antiproton. Anyone want to answer this? A. Yeah, it's straightforward, right? Charge. So so it has positive, and this is negative. So the net charge here is 2 plus, but here it is 0. So charge is not conserved. So then tell me, how can we produce an antiproton? By colliding two protons. Anyone know? We have two protons colliding. But you have two protons. How do you do pair production? What will be the reaction? Can you tell me? P plus going to what? 3 protons and 1 antiproton. Oh, okay. Why not 5 protons and 1 antiproton? Is that possible? Is this possible? Or you can go on like this. What? Baryon number. Okay, yeah, you're right. Because antiproton has barrier number -1 and this one is plus. So yeah, the barrier number should also be conserved. Yeah, so this is not okay, but yeah, this one can happen. So what you do is you collide the protons with a much higher energy, and then you can get the two protons back and then a pair of protons and antiprotons. So yeah, that's how you can create antiproton. Okay, so then the last problem today. So we can get high energy neutrons through which of these accelerators? Anyone has any idea? DC accelerators, nuclear reactions, spallation reactions, or fusion process? Have you all heard about this, all the four processes? So DC accelerator, not about the third one, right? So yeah, that's why this question is here. So yeah, the correct option is third one. So in the spallation reactions, what we do is we take a very high energy proton or neutron, mainly proton, okay, and bombard it on a on a metal foil or something which has many nucleus embedded, and so what it does is, so as I mentioned in the starting, so if you have a very high energy particle, it will have a very low wavelength, low de Broglie wavelength, so that it can go inside the nucleus. So it will just probe inside the nucleus and interact with the nucleus and destroy the nucleus basically, and so you will get in the output what you will get is protons and neutrons disintegrated from the nucleus, and so then you will have very high energy protons and neutrons flying away, taking the energy of this initial particle, because the kinetic energy gets transferred into these fragmented particles, and so you have neutrons, protons, many neutrons, protons from the disintegrated nucleus coming out, and so you can maybe collect the neutrons, and you can have very high energy neutrons that you can use in various kind of applications. Okay, so mostly I think the material scientists use neutron diffraction to determine properties of materials and things like that. So yeah, so that is called a spallation reaction. Okay. Okay, so yeah, that's all for now. Thank you. But before you all go, anyone has any general question, anything you have to ask, you can ask, and yeah, and what are your you can give me some feedback, like was the set of questions were very elementary, or did you enjoy them? Was it okay? Okay, so anything you want to ask? So the NPTEL lecture, so you can go yeah, so you can if you have enrolled for the course, you must have got an email with all the details, right? So you maybe want to check your email. You must have got all the relevant information. So, or if you don't have if you can't find it, you can just search Accelerator Physics NPTEL in the Google, and it will take you to the NPTEL page of the course, and there you can have all the lectures. Okay. Yeah. Anyone else? So yeah, one more thing. So these slides will be uploaded to the website of NPTEL, and also the recorded lecture, recorded session, this all the sessions, so you can revisit it if you want. And yeah, anything else? Hello? Yeah, okay. Uh, so on this, on that website, there are various lists of books. uh, Maybe you can go through them. And yeah, and first I'll suggest you to go through the lectures, because I mean the professors have really like explained everything very basic, so maybe you'll find that helpful too. And if you can't follow them as well, then you can go through the books. Okay. Yeah. Okay, any other question? uh, okay, if not, then I'll see you guys again next Saturday, same time. And okay, bye bye. Thank you for joining.